Now calculus on manifolds. This is the main attraction of this lecture. We want to develop calculus on manifolds, and for that we will need to develop some tool. And the reason we are interested in differentiable manifolds is because we can use the calculus defined in, let's say, some n-dimensional Euclidean space to which let's say the manifold is homeomorphic to or locally homeomorphic. So we can use our previous knowledge of Euclidean calculus on Euclidean space to define the calculus on manifolds. And the smoothness of the map ensures that the calculus is independent of the coordinates. So first tool that we will need is something called a differentiable map. If I define a map from M to N, where M is a manifold and N is another manifold, and they have the dimensions of small m and small n respectively. So let me write that down. So dimension of M is small m, and dimension of N is small n. So if I can introduce such a map that take elements of the manifold M and it maps it to elements, it maps those elements from M to the manifold N such that any point P on manifold M goes to f of P, and your f of P will belong to N. Then F has the following coordinate representation: psi composed with F composed with some phi inverse from the m-dimensional Euclidean space to the n-dimensional Euclidean space, where chart on M is written as u phi and on N it's written as v psi. Now let's try to see this in a picture. Let's say this is my manifold M, this is my manifold N, this is the n-dimensional Euclidean space, this is the m-dimensional Euclidean space, and we want to see what does this map does, this psi f phi inverse 1, right? So we define chart u phi on M. So phi takes any point from the manifold and maps it to the Rm, right? This is phi. So what does phi inverse does? It takes a point from Rm and maps it to the manifold. That means if you supply the coordinates, then you know what's the point on the manifold by using phi inverse 1. Then what happens is that we see that F is acting on it, right? So F, what F does is that it takes this point, let's say P, this is the point P. What F does is that it takes it from P to f of P. And then finally on N we defined the chart as V psi, where psi's were the local homeomorphisms. So what psi does is that it takes the point f of P and then maps it to the n-dimensional Euclidean space. That's what the action of psi f phi inverse 1 is. That is, it takes points from Rm to Rn. And in simpler notation, we can write this as as some y equals to f of x, where x are the coordinates on Rm and y are the coordinates in Rn. Okay, and if this kind of a map, that is y equals to f of x, is smooth or say infinitely differentiable with respect to all the x's, that means all the x that belongs to Rm, then we call them differentiable at a point P. Okay, so if I write, if this y equals to f of x, or instead of using this simpler notation, you can even write it as psi f phi inverse 1 that initially starts from some x is C infinity. This is how we denote smooth. The word smooth can be denoted by this C infinity. If this is smooth with respect to all the x mu's, that means x1, x2, x3 dot 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 up to xm, then we call f is we call f differentiable at point P. We require this differentiability in accordance with the smoothness of the transition function. And we should also keep in mind that this differentiability is independent of the coordinate system. Now, this type of maps are actually called differentiable maps, because you saw that the map we are defining like this from m to n, we require that it has to be differentiable, or so to say it has to be smooth. So these are the maps we are calling differentiable maps. Okay, so from one differentiable manifold to another, we can always define a differentiable map. And the comment I made a few seconds ago is that it is independent it is independent of the coordinate system, and that can be proved by showing that this differentiability of f is independent of the charts in the manifold n. And you can also approach the problem in another way, is by doing the following. This, let's say, consider two overlapping charts on M. Let's say this is M, and these are two overlapping charts. Let's say one is U1, another one is U2, endowed with phi 1 and phi 2, like this. These are my charts, and my P belongs to the intersection of these open sets. And according to phi 1, the coordinates of P will be, let's say, x mu 1, and according to phi 2, the coordinates of P would be x mu 2. Okay, now if I express the point P in terms of x1 mu, then the map F, which takes P to the manifold N, takes the following form. So when we express F in terms of x1, we have the expression of f as some psi f phi inverse 1. Again, what was psi? Psi is something that takes your f of p and maps it to Rn. Okay, and if I start with the coordinates x2 mu, that is I'm taking the homomorphism to be phi 2, then for f it's written as some psi f phi 2 inverse. But we can write psi f phi 2 inverse as the following: psi f phi 1 inverse composed with phi 1 composed with phi 2 inverse. So it's like I used the fact that phi and phi inverse 1, when composed with each other, they give me the identity map. Alright, and these maps are it can be popped out in between these two, and we note the fact that this phi 1 phi 2 inverse 1 is nothing but the transition function between these overlapping regions, right? And this is what this is by definition smooth. So this is by definition smooth. So this whole thing has to be smooth regardless of the coordinates. And you can even do this in a simpler notation. You can start from, let's say you are defining this map as y equals to f of x1, okay, but in the overlapping region you can also write x1 as functions of x2, so you just put that back in, so y can be written as f of x x1 of x2, right? But then again, any transition between x1 and x2 is by definition smooth. So the arguments are smooth and it has to be smooth as well.